If you're building any kind of modern software today, we're talking AI, graphics, huge simulations, you're not just slinging code around. No, you're actually manipulating high-dimensional space. And to pull that off, to really do it well, you have to speak the language that shapes our entire digital world. And that language? It's linear algebra.
In this quote, this really gets to the absolute heart of the matter. We have to, completely stop seeing a matrix as just a boring grid of numbers in a spreadsheet. The real magic, the power, it only unlocks when you start seeing it as an operator. Think of it as a tool that can literally stretch, rotate, and just fundamentally transform information. That's the huge mindset shift we're going to dig into.
All right, first up, we're diving into this idea of a new reality, looking at how we jump from just writing code to actually shaping these massive high-dimensional spaces.
Then we'll get into this awesome concept, reduction versus expansion. It's all about the duality of vector products.
So check this out. This is that duality in action. On one hand, you have the inner product, which takes two vectors and just squishes them down into a single number that tells you how they relate. But on the other hand, the outer product does the complete opposite. It expands them, building a whole new matrix, a brand new structure. You see, it's this constant push and pull, reduction versus expansion. Let's break them both down.
Okay, the inner product. I like to call this the engine of similarity. Seriously, it's the powerhouse chugging along behind every single neuron activation in a neural network, every weighted sum you can think of. You know, when a facial recognition system scans your face and checks it against a database, what's it really doing? It's using this exact principle. It's measuring the alignment between feature vectors to find that match. It's all about finding that resonance, that connection between different pieces of data.
And then you've got the total opposite, the outer product. This is the engine of expansion. Its job is to build up structure from really simple parts. A perfect example of this is something called singular value decomposition, or SVD. It's a pretty cool technique that can take a super complex matrix and break it down into a sum of these simple little outer product matrices. This is literally how image compression works. You can basically rebuild a whole image just by adding these fundamental layers back together. So if these products are building blocks, how do we actually use them to solve really complex systems?
Well, we do it by peeling back the layers, and the tool for that is Gaussian elimination. Now, hang on, I know what you're thinking. Ugh, tedious high school math, right? But trust me, we're going to reframe this. We're going to look at it as a really powerful process of discovery. So here's the key thing to get. Gaussian elimination isn't just about grinding through equations to find x. No, it's way cooler than that. It's about taking this big, messy, chaotic system of equations and just methodically untangling it. You're peeling back one layer after another until the core logic, the actual solution, is the only thing left standing. And how does it do this untangling? It's all done with just three simple but really powerful actions. First, we can scale rows, multiply them. Second, we can swap them, move them around for a strategic advantage. And third, and this is the most important one, we use elimination. That's where we add a multiple of one row to another with the specific goal of creating zeros. We systematically wipe out numbers until we're left with this clean, simple upper triangular form. That methodical process is what finally reveals the hidden structure inside. But there's a big problem here. Doing that whole elimination process over and over again, it's what we call an O(n) cubed operation, which is just incredibly inefficient. It's a huge waste of compute power. We need a smarter way, a better blueprint. And that, my friends, is LU factorization. LU factorization is, and this is just brilliant, it's basically a recording of the entire elimination process. It's like you hit record before you started. So instead of just throwing away all those steps we took, all the multipliers we used to create the zeros, we carefully store them. We preserve the complete history of the transformation. Why? So we never have to do all that heavy lifting ever again.
And this is what that blueprint looks like. A equals L times U. So original matrix A gets split in two. U is that nice, simple upper triangular result we worked so hard to get, and L, that's our recording. It's a lower triangular matrix that stores the exact steps, the whole process. And by separating the process from the result like this, we can now solve for new inputs with a much faster O(n) squared operation. It's a huge win.
And this is why this all matters to you as an engineer. I mean, this whole idea of separating the structural analysis, the how, from the specific data, the what, doesn't that sound familiar? It's a core principle of great software architecture. We do this all the time when we separate business logic from our data models. Turns out, linear algebra got there first.
So where does all this lead? What's the big picture? Well, these blueprints, they're not just abstract math concepts. They are the invisible engines that are literally powering our modern world.
I mean, just think about it for a second. When a neural network learns, what is it doing? It's just tons and tons of matrix multiplication. What about the physics in a video game? Every single time two objects collide, the game engine is solving a linear system right then and there, in real time to figure out what happens next. You've got high-frequency trading, complex CAD software, mind-blowing ray-traced graphics. Every single one of these is built on the exact foundation we've been talking about.
Honestly, this is the perfect way to think about it. Grasping these principles isn't about memorizing formulas for a test. It's about being an architect who deeply understands the physics of the materials they're building with. And knowing that, that's what lets you build software that isn't just functional, but is truly efficient, scalable, and rock solid.
And all of this leaves us with one final big question. We've seen how these amazing blueprints help us manage incredible complexity. But let's be real, our data is only getting bigger, faster, and way more dimensional. The tools that work for us today, well, they might not be enough for tomorrow. So the challenge, really for all of us, is this. What is the next great blueprint that we are going to need to design?